Morning, everyone. This is Shauna, and I'm here with another video to help you with some of your homework and maybe help you with the exam review. I'm going to be talking in this video about L'Hopital's rule and correcting some misunderstandings from the last lecture that we had on L'Hopital's rule, indeterminate forms, and a little bit on inverse trig functions. I'm not going to be covering inverse trig functions in this video, however. So let me remind you of something that we saw here in the slides for the lecture. This is example 1, and it says find the limit, use L'Hopital's rule where appropriate. If there is a more elementary method, use it. If L'Hopital's rule doesn't apply, explain why. And we can see from the example here that Professor Nickdell plugged in the value of -2, and she shows that, in fact, this quotient is indeterminate. It's 0/0 form. And so she proceeds to take the derivative of the numerator and the denominator and get the limit. However, there is another way to do this, as there often is with limits. Sometimes there's more than one right way to, to do these things. And if you look at the other format, I wanted to make sure you were aware. I'm sorry, I believe I lost connection here. As I was saying, even though we can see that L'Hopital's rule applies, and I'll go back to that. Even though we can see here that L'Hopital's rule applies in this situation because she was able to plug in the numbers and get the limit, we can also factor. So here, if you'll notice, this expression can be simplified, and all I did here was factor this polynomial at the bottom by our elementary methods. We want factors of 2 that give us 3, which are 2 and 1, both positive because the middle term is positive. We cancel the factor on top with the factor below, and we end up with the limit as x approaches -2 of the quotient 1/x plus 1, which we can then evaluate by direct substitution. So I proceeded in the usual way as we did in Calc 1, and we get, I evaluated, and I forgot to show that evaluation, but this would be, let me put it on the screen. If I were to evaluate this, this would become 1 for the top over -2 plus 1, which is -1, which is the same limit that Professor Nickdell got when she evaluated. So just wanted to make you aware of that. The other thing that I wanted to show you from the slides, let me go back to this. The thing that I wanted to show you from here is that on example 7, I believe it was example 7, let me check. Let me scroll down, bear with me for a minute. It was actually example, yeah, it's example 7 right here. There's an error here, okay? Find the limit. I believe this has since been fixed, but the limit as x approaches 0, this limit is correct. However, the form is not indeterminate. And let me show you why that is. So in this case, we have, let me share the screen. Let me go to new share. We're going to share this, but I'm going to show you the second page of this. Here I've graphed for you in a very crude way. I graphed the cosine on the interval from negative pi over 2 to 2 pi in increments of pi halves. And I've graphed also over it the graph of the secant. Remember, secant is the reciprocal of cosine. So what you see where the dots are is the cosine curve. I didn't draw in the cosine, I just drew the dots where it would be, and proceeded then to draw the cosecant over it. As you can see, I'm sorry, not the cosecant, the secant over it. This is a secant curve. As you can see, as we approach 0 from the right, so we're approaching 0 from this part here. We're approaching 0 from here. That limit is 1. So this becomes 0 times 1, which is not indeterminate. So this becomes, let me come back. The square root of 0 times the secant of 0, which is 0 times 1, which is 0. So again, the limit was correct, but the form is not indeterminate. Just wanted to make sure that you had seen that in case you missed the video where we discussed it in the class. That video is available. It should be available to you. The next two problems are from the homework section, R5. And these are two questions that I got more than once. One is number 11, the limit as x approaches infinity of ln x over, minus x, ln x minus x. And again here, this is the form infinity minus infinity. When we have that, we tend to need to make a fraction from it. So we have ln x minus x, which is what I have over here already. Remember, there's an imaginary 1 under here, so I'm going to multiply by the conjugate of what I have, which is ln x plus x. And so I'm multiplying the existing term by ln x plus x, and I'm putting 1 on the bottom because I'm multiplying by 1. So I'm not changing the limit, I'm changing the way it looks. So here, I apply the distributive property, ln x times ln x. Be careful, that's ln x quantity squared, not ln of the argument x squared. Careful there. And then the middle terms, as we know, cancel. So I have minus x times positive x is minus x squared. And the bottom is ln x plus x. Okay, that's the first piece of this. Now, here I have infinity, right? Minus infinity. And you might be thinking, okay, what do we do now? But ln of x quantity squared, it's going to approach infinity, yes, but it's going to approach infinity much slower. If you think about the way that ln of x looks, ln of x is very flat, especially going toward positive infinity. It increases, but very slowly. Now, negative x squared is going to tend to decrease if since it's negative, it's going to decrease. X squared is going to be very positive, and it's going to increase faster than ln of x squared. So this term at the top, this limit goes to negative infinity, which is why I put that there. It's not necessary to put negative. I just wanted to remind you that this limit at the top is approaching negative infinity. Now, the limit at the bottom we know is approaching positive infinity. So now we can apply L'Hopital's rule. The other thing here that is a struggle for some of you, when I differentiate ln of x quantity squared, I use the power rule. So I get 2 natural log of x to the first power, but then I have to differentiate this inside function. It's a composition. So I differentiate ln x and get 1 over x. Don't forget the chain rule. Then I differentiate x squared. So negative 2x, and we do what we normally do. Now, resist the urge at this point to blindly apply L'Hopital's again. Check your format. So if you were to think about x approaching infinity, 2 log x is going to approach infinity. This term, 1 over x, is going to approach 0. So this product, this 1 over x approaches 0 faster than 2 ln x approaches infinity. So it's going to be dominated by this term. And that limit is going to approach 0. So 0 there. And then this 2x approaches infinity. So I have 0 essentially minus infinity over 0 plus 1. This is not indeterminate. So here, we have a limit that's approaching negative infinity at the top and a limit that's approaching 1 at the bottom, which means that the limit of this quotient is going to be negative infinity. Okay. The other one is problem 12, and I made a little bit of a bigger deal out of this than it needed to be if you came to see me. This is very similar. 3 to the x minus 2 to the x over x. Again, it's the form infinity minus infinity over infinity, and I wasn't sure if we were supposed to somehow show that this, it's fairly apparent from either looking at the graph or thinking about what you know about the behavior of these functions, that if x is going to infinity, 3 to the x is going to approach infinity faster than 2 to the x. So this faster approaching infinity means I'm going to approach positive infinity, right? So even though this top piece is indeterminate, this approaches infinity faster. And this top does approach positive infinity. And we have infinity over infinity. So we get the limit as x approaches infinity. Here, I'm going to take the derivative, and I'm going to get 3 to the x natural log of 3 minus 2 to the x natural log of 2 over 1. And this limit is infinity. I hope that helps you. And I hope that you're able to do more problems. I will see you in my next video and in class later in the week. Take care of yourselves, study hard, and I'll see you next time. Thank you, folks.